Today, my talk and presentation is going to be about the drivers of innovative facade solutions, and we'll be looking at the things that essentially steer development and technology and innovation one way or the other in the facade industry. A little bit about Meinhardt, a global company. We've got over 47 offices worldwide, a great number of staff, 1,500, a 60-year plus track record. And just for location wise, we are in, these are the locations in the world where we currently are. We have quite a few offices in the Asia, Australia region. That is where we're mostly mostly available at the moment, and then in Europe we have just a few offices elsewhere, but we are growing and taking the world one region at a time. So I'll just move on to my presentation now. So what is technology? This can really be defined as the scientific application of scientific knowledge for practical purposes, especially in industry. It can also be defined as the science or knowledge putting into practical use, to solve problems or invent useful tools. It is continually developing results of accumulated knowledge and application in all techniques, skill, methods, and processes used in industrial production and scientific research. So these are just three definitions of technology, but what this in essence says is technology is innovation. Sometimes we tend to see technology as a physical tool, but sometimes it could also be a process. But any process that causes adaptation, any process that causes innovation can be deemed to be a technological advancement in that sphere where its use has, enacted some form of, it solved a problem or mitigated an issue. So technology is basically the look at the innovative process. It could be very intentional in a sense whereby, we identify a problem and, you then have a definite aim and a deliberate attempt to actually try and solve that problem. There is a clear search for, how that problem is solved, or if it cannot be solved, how then do we mitigate or reduce the impact of the problem. And it could also be a case of where there's a process or a innovation already existing, but then it's the next step in the evolution of that innovation to make it, better, to make it more efficient in a way, and then that gives us a solution. Now, it could also be accidental, wherein there are a number of elements which have really been, gotten by mistakes. There are a number of products which have created big impact in our development as human beings generally, but if they've generally come about as a mistake. So for example, PVB, for example, wasn't an intentional technological solution. It was developed as an error, and then further research went into looking at it to see how can that then be applied in one way or the other. And it first of all gained traction in the automobile section, and then it then migrated into the building industry to being laminate glass as we know it today. So with accidental inventions or accidental innovations, we look at things like, cross-industry applications of a product, of a process, unforeseen side effects of inventions. And, that then gives us a cyclical approach of where, things are invented. Once they've been in the market or they've been used for a while, we understand it better, we understand where it doesn't quite work out, and those areas then give us additional opportunities for invention and re-improvement. And basically, so the invention process and innovation process is really cyclical, and it's never really ending. You know, there's always something to improve in a product or in a process, and that is how, you know, I would put the process of innovation. So what drives innovation in facade? So I've tried to, there are a lot of drivers, and we'll just be focusing on just a few, but just to give a quick overhead of how things generally stand. So we start with performances. You know, the facades generally has a lot performance, you know, to give from the, you know, previous speakers. If we look at just the performances, you know, the facade has to deal with the thermal, the acoustic, climatic issues, geological issues, accidents or disasters. You know, it needs to be secure. Depending on the region, you would have different social or cultural aspects to deal with. It needs to be safe, it needs to be sustainable, and it really needs to, you know, work into the future. It needs to be future proofable, because you have that longevity of where buildings are, you know, 60 years old. I mean, in many of our countries now, we've got buildings that are, you know, easily 400 years old, you know, 100 years old, and things like that. So these buildings are a very much permanent stock of civilization, and how they go forward in how they age and what they will look like in 100 years time or 60 years time really needs to be put into context. Then we also look at processes. So in processes, we basically deal with the fabrication, manufacturing, handling, transportation, you know, the design processes, the construction processes, dismantling, you know, and how it's, you know, the safety, dismantling and recycling, and the end of life use, and how those are managed. Drivers can also be as a result of legislation and policies. So this is in case of in building regulations, design codes, safety codes. Insurance policies can drive innovation in one way or the other, and future-proofing accidents and disasters, which, you know, will fit into how legislations and policies evolve over time, and that would affect, you know, the direction in which innovation in the industry is going. We also have cross industry innovation, wherein it might not necessarily, some product or process or material was probably developed for, you know, other industries, you know, either the aviation, automobile, aerospace, energy, MEP systems, and the like, you know, but they would find application in the facades, or it could be as a result of certain, so if we use MEP systems, for example, you know, certain innovations in how efficient mechanical systems, you know, heating and cooling can impact on the facade, on what, you know, how hard the facade works, or how those, you know, certain other performances or innovations in the facade industry can impact MEP systems. So there's really a tug and a pull relationship between all these factors. So if we're going to focus on the physical performance drivers, I've sort of split these into like four broader areas, where we've got comfort, serviceability, aspiration, and safety. So with comfort is very much physical comfort we look at, and also the psychological and mental sense of comfort as well. So if we're looking at the physical aspects of comfort, you know, it's things that are more they're tangible, or they're measurable things, you know, physical senses, your sight, your sound, your sensations of heat and cold. For the sight, you look at things like glare, visual acceptability, how the aesthetics, transparency. And for sound, it's, you know, the acoustics, the airborne, and also vibration. And all these, and with the sensation is heat, cold, damp, you know, thermal insulation, how thermally, you know, insulated the material, a facade will be. And then for psychological is more of a perception, wherein, you know, individual phobias and fears and aspirations of safety or paradigms of safety or come into play, and that obviously needs to be designed. So for example, with a psychological one where as buildings are getting taller and taller, you know, you can have a glass balustrade that has been designed to death to be as safe as a rock. However, you know, somebody who's got a maybe fear of heights because of the transparency might feel unsafe. It's not that the glass isn't safe, it's just that there is a perception of it not being safe just due to the fact that it's glass. And, you know, we have a mental assumption that, you know, glass breaks and you know, it's transparent. You can see 40 stories down the, you know, the view. So that has an impact on how that element is viewed. In terms of serviceability, it's really down to the processes, you know, the integrity, robustness, the bespoke solutions for certain individual elements. You know, that also comes into how it is used in a social context and in a cultural context. And it also deals with things like adaptability and inclusion of people with disabilities, how they're able to experience spaces, how they're able to operate. So windows, for example, and, you know, this goes into operability and ease of use. And also a big one is cost, because cost is a big driver in terms of affordability, in terms of the cost of processing things. So if a material is so expensive to produce, it really needs, you know, it probably will not gain the traction that it could have if it was in a bit more affordable. And cost is a big driver because, I mean, most clients, most developers have a cost in mind when things are being built. So if the technology is above the cost margin, it's very likely that, you know, the technology of the facade to make it what it should be might be prohibitive to the development of it. So aspirations is one where it's also sort of falls under sometimes the psychological or mental state. But, you know, it's the aspiration of, you know, human beings, we always push the boundaries. I think we're sort of created to create and improve. So it's like, how can we make it bigger? How can we make, you know, things thinner? How can we make it greener, more durable? How can we improve the design life? How can we make it more cost effective? You know, these are all questions that will push the performance and drive, you know, innovation in one way or the other. And then the last bit here is safety, where, you know, the facade needs to be safe, the processes need to be safe. It needs to provide the containment as it should. So for example, for walls or balustrade, the integrity needs to be there, but sometimes in terms of failure and in terms of just day-to-day serviceability. It needs to prevent injury. So if it should break or it should fail, you know, it really needs to be designed in a way that will prevent injury and also aid rescue. So, you know, the facade shouldn't necessarily be, shouldn't contribute overly to, you know, complicating a rescue aiding scenario. And obviously the processes of not just manufacturing, but also construction and it being in use, replacement and things like that. So all of these will factor into different ways in which, you know, the facade drivers go on. So also the interactions between each of these drivers is very much interconnected. You know, it's multifaceted. Each driver is connected to the other. Once you pull one in one direction, it would sort of, you know, either diminish or enhance certain aspects of other drivers. So there's really needs to be this equilibrium and balance between all the elements to do what it needs to do. What this then results in is looking at, you know, if you look at one facade element, it has numerous diverging requirements and conflicts, and, you know, it's one thing needs to do like 300 different things, and it's trying to get that balance, you know, to get it in the position where it's fit for purpose and it's meeting the design requirements that it needs to have. So if we look at a few of these said conflicts, and I'm sure many would appreciate, you know, we want light transmittances, but we also want it to be insulating. In one element, you want it to be natural ventilated, but you want it, you know, to keep out the sound, to be acoustically, to work acoustically. You know, these are all very conflicting elements. And, you know, so where we've got in sort of the temperate regions, particularly where you've got great swings in summer and winter temperatures, you want it to perform basically like a Bedouin tent in summer, but you also want it to perform as insulated, you know, like a cooler, and keep the heat in winter. There is also the conflict of transparency, where with the progress and the innovation in glass, in modern glass fabrication, we want, you know, in one part we want the transparency of the glass. However, we still want that same glass to offer absolute privacy, and each of these conflicts have brought about with, you know, some fantastic products. You know, it's the electrochromic glass has come about as a result of some of that. In with the ventilation and sound elements, I know certain companies are looking at, you know, glass window systems that allow trickle venting, but still provide a level of acoustic insulation. So we also want it to do the glass to be as open as possible. So in this image, we've got level threshold here, which is a requirement for disability access. So if somebody's on a wheelchair, you know, they can access external spaces, balconies, terraces, without the rebates that sort of, you know, it should be leveled, the internal spaces and the external spaces, to aid, you know, the flow of wheelchairs or other mobility appliances. But we also want it to be, as you know, very, very weather tight, you know, as weather tight as a submarine. And, you know, there's a huge sway, or huge sway in the development of door systems and the threshold details to be able to allow that. But at the moment, we're not quite there yet, wherein, because the level threshold doors don't necessarily perform as great for weather tightness, particularly water tightness. So it's really difficult at the moment to get high performing doors. But that is a thing that I know that, you know, system providers are looking at. The other one here is we want it to be very, very secure against any intrusion. However, the facade still needs to act sometimes as emergency exits, you know, in the event of whatever catastrophe might be it a fire or anything that might need emergency exit. In another point, you know, we want it to be elements to be user friendly, especially operable elements. So if it's, you know, blinds, windows, doors, and things like that. But you also want it to be free from abuse, you know, for, you know, which you can design up to an extent, but you can't really, you know, fathom or think about all the wonderful ways, you know, people can use things wrongly. And as the last sort of set of images, we really want the facade to do a myriad of so many different things, to be perfect in all, but also to be as cheap as chips, as they say. And that is a proper conflict, because obviously there is a lot of for it to do all the things it needs to do, there is usually a cost implication. So, but having to get that cost balance without having to reduce the amount of performances or dumb down the system is a big challenge. That's why I think there are a number of images where you see the client's budget and the client's brief, which doesn't quite match up. So that is obviously one of the drivers and one of the conflicts that we need to consider. So I'll be doing a very brief case study of how certain things can affect the trajectory of innovation and how technologies are used. So if using the Grenfel incident, which happened 2017, I believe, 20 summer. And so that was a fire of a tower block in London. And this is basically, there were errors everywhere, but obviously the facade did contribute to a significant extent to how quickly the fire spread. Based after this disaster, losing not just the entire building, but also a significant amount of lives. I mean, in these incidents, even one life lost is one too many. And I believe there were about 75 deaths that were accounted for in this in this disaster. This then led to a big review of the legislation around cladding, around what was allowable in the in building systems. And this then obviously led into how buildings are designed generally, the classifications of different building types, high risk buildings, residential elements like hospitals, where if there was a fire, how is the cladding then impacting on the fire loading on these structures. So it's changed everything, including construction materials and products, what you can use, how you can use it, the interactions with other performance requirements. So basically the fire performances has basically is the predominant driver at the moment. It can perform as great as it can. If it doesn't have the right fire rating, you can't use it on the buildings. It impacts construction methods, even methods that were more or less cast in stone. We've always done it this way. It's tried and tested. We've not changed anything in the last 20 years. Everything got shook up. The serviceability of the material, safety in use, it impacted on the financial market, the legal systems, and the building regulations. So these are all the impacts of which this one incident has had on the UK construction industry, and especially the cladding industry. So just to show a few instances of a few areas of where how this has impacted us. So for example, certain buildings, you're not allowed, and certain height, above a certain height, you're not allowed to use anything other than mineral wool, or any, basically has to be A1 rated for fire. This has, removed out a lot of the PRI, polyurethane and other sort of better performing, but in terms of thermal, but not necessarily in terms of the insulation, in terms of the fire, has taken them out of circulation. So Calostat and mineral wool is basically your options. However, Calostat, as great as it is, it's still quite financially prohibitive to for many people to use it whole scale around the buildings. But it does have its use in smaller, maybe smaller areas that just we don't have the zone to stuff it full of mineral wool. It's also brought about the use of laminated glass on balustrades, and at the moment, because the typical PVB, EVA, and Century glass, they do not meet the A1 requirements, so you're not able to really use these on balustrades. So at the moment, there is a sort of the transitory period where, you know, glass balustrades is what do? You cannot really use monolithic glass, because if you're building a 40-story tower, you know, a monolithic toughened glass is still subject to breakage. And if you don't have the laminating to keep the integrity and the containment, then, you know, it's moving away from certain design. So it's also, you know, it's affected things like brickwork. You know, brickwork has been a staple in the UK industry for ages, and it's affected how brickwork is built, you know. So the cavity tree, which is shown by this panel here, has always been a plastic, a rubber material for its flexibility. That's not, you can't use those anymore due to the fact that many of them are flammable. This has then pushed manufacturers to look at other non, you know, flammable A1 rated materials. So you know, it's come the versions which now have stainless steel versions. There's zinc versions that have come about now, and this has all come about in the last, you know, 3 or so years. Which, you know, we're very happy to tinker along with the rubber and the plastic sheets. There was no issues with them up until, you know, the regulations changed. Also for the coating of metals, you know, even the coatings down to the coatings of metals are specified as not being, you know, they must not add to the fire load. So A1 rated or perhaps A2 rated PPC coatings. So we know that some of the PPC coaters have, you know, fire rated coatings which can meet these standards. And is also a look at how we generally build, how we design, how we assume fire would spread, you know, in terms of cavity breaks and cavity barriers. It's also impacted on how we define a cavity. What is a cavity? At what point do you stop the fire stopping in a facade, in a curtain wall system? And all these elements are being reviewed. In terms of general documentation, it's the approved document B in the UK, which is the fire safety document regs, has been completely overhauled. You know, it's spawned the review of the building safety bill, which looks at competencies in the industry, and it's also affected, you know, the PIs of many in the facade industry, in the building industry. And this is not just facade consultants, it's not just main contractors, it's you know, it's subcontractors, it's facade consultants, it's architects, it's fire engineers. Everybody who's involved in the cladding in one way or the other has been affected in one way, shape, or form, with astronomically high PIs in the last, you know, 3 years since the fire. And this has also affected even the end user in terms of mortgages, whereas, you know, certain buildings suddenly are not mortgageable. So some people can't sell, some people can't, you know, they can't really, it's really messed up the system. Whereas, you know, the mortgage providers are asking for certain guarantees that, you know, the building was built in a certain way. But obviously anything that was built, you know, I'll probably say 2019, before 2019, wouldn't necessarily have all the things that, you know, are being asked for. So, you know, you've got developers in a pickle that may not be able to sell their buildings. You know, you've got them having to go back retrospectively to do some remedial work. So this is the sort of things that have, you know, impacted on how things are looked, where a more critical look on the development of systems and how we build and construct it's given us that is put a lot of impact on that. It's just unfortunate that, you know, it had to be a disaster to sort of spearhead this sort of change or this sort of review. But generally worldwide, not only in London, you know, it's disasters have a very uncanny way of shining harsh lights at what we can do better and spearheading innovation in that sense. So
I I think we left with 1 minute. Sorry.
Okay, brilliant. I'm just going to run through sustainability. So
Sure.
with sustainability, it's just a quick headline view of, that is the new driver, I think, with the Industrial Revolution. I think of it as the new Industrial Revolution, where, there's net carbon zero, there's, trying to stop the global warming and reduce the carbon footprint. Typically, these are the intent, the processes, and the targets, and each of these elements, with the intents, impact on how different things are being manufactured, how electricity is being generated for the fabrication, how we use materials, how we design. We need to design more efficiently. And if we look at the processes, each of these processes has a potential for impacting how the industry, the building industry, goes into its next phase. And each of these elements, from producers to manufacturers to end users, there are huge sways in how technology is being developed to assist in getting more sustainable design. And hopefully, the end product is to get to a point where we can adequately calculate how much carbon is being used in our buildings, in our processes, and to get to a unified and agreed element where we can say for certain. I know now there's still a little bit of dispute in how this is calculated, but I think we're getting to a cohesive point in time where we're getting into how this all gets to a unified element that we can all agree on is the way forward. So this gives a broad heading. And so where do we go to from here? Ideally, we would like to think that, the sky is the limit for technology and innovation, and in a way it is. However, it's really more like a game of snakes and ladders, where we just keep tinkering on, and then we hit a major milestone, which, like a ladder, which, lifts you up years in advance. But we also need to hit some snags which set us back, and then we have to then revise and look at things again with fresh eyes constantly, and then we've continued the process. Thank you very much. I think this is me done.